Okay, so welcome everyone. So this is the inaugural of the public lecture, like the first public lecture. And as I was telling John, like 6 years back in 2018, we started a Foundation of Data Science series, or like that was a virtual talk series. And we also invited John to start that series. And this time as well, like for this public lecture, John is our first speaker, and we're really honored that he could come here and do this talk. I actually don't know how to what can I say for to introducing John that kind of reflect what the amount of enormous contribution that he has in the field. Like when I was an undergrad student back in 2004, 2006, during that period, like my view of computer science was very much confined to textbooks, right? And I didn't know much about research and all of that. And there were only few people at that time who I have heard about, and one of them was Jon Kleinberg. So many of you who are coming from much newer generation, but I'm pretty sure you know about John's work from wave search, from the small world separation, from the six degree separation, small world phenomena, and so on. So John has done amazing foundational work during the period of web development, social network formation, and so on, evolution, and so on. So anyway, so Jon Kleinberg is a Tisch University Professor at Cornell. He has won numerous awards, like whatever award you can think about. He has won that. Sloan, Packard, MacArthur. He's a fellow of National Academy of Science, National Academy of Engineering, NAE. Yes, like whatever award you can think about, John has won that. Okay, so I have to look at the list and I can read through the list, but you can look up his Wikipedia article and see. And I don't Nevanlinna, what else, John? Like, is there any award that you haven't won? Anyway, we are really honored to have you here. Welcome.
Thanks very much. All right, thank you. Okay, well, thanks. Yeah, thanks very much for the invitation to come speak here. Thanks for the kind introduction. Nice to see so many of you who I see and have seen on past visits to UCSD. I always enjoy my visits to UCSD. I think it's been 6 years since I was last here, but it's really a wonderful environment, a wonderful community. A lot of people whose work I have enormous respect for. And so, yeah, I was thinking about sort of what to talk about in this kind of sort of general lecture about sort of these broad issues in computing and data science. I want to talk about some work I've been doing with a number of people. There's sort of two projects that kind of represent two sort of sides of things. But I'll start with some joint work with these last two people here. My longtime co-author, Senthil Mullainathan, who's a behavioral economist, who's moved to Chicago at MIT. And Manish Raghavan, who was my PhD student who graduated 3 years ago and also is at MIT now. And we've been interested in trying to come up with sort of simple models that are at the boundary of sort of simple theory of computing models merged with simple models from behavioral economics and the behavioral sciences to try to get at some of the experiences that we have in the online world. And I'll try to sort of develop those as I go. Obviously, there's a lot of, turbulence in our present time, technological and otherwise. And, part of what we were sort of hoping to do in this work that, really began sort of 4 years ago was to sort of think about how kind of the collision of technological issues and some behavioral issues kind of might help speak to some of those questions. So the setting for all of this is going to be the online world. If I think about the online world, it's like this little keyboard. So the setting for this, oh, I see the problem. This whole thing is shut down. Okay. Hold on. We're gonna stop sharing. See if we can wake it up. That's me. Here. That's this. Okay, there we go. So, okay, the setting for this is the online world. And you know, if you think about the web has sort of always been sort of balanced between these two metaphors for what is the web, right? You know, this experience that we have when we go online, when we engage with others about all things. You know, one is, I think in its early days, this idea of like the vast universal library of all human knowledge, whose basic units are things like pages and hyperlinks and associations that form the associative memory of the web. And then balanced against that, the theme which really kind of came out maybe 10 years after that was this metaphor of the crowd, right? This teeming mass of people who react in real time to things that they happen. You know, and again, the basic units of that are the individuals and the sort of contagious way that things spread between individuals. Now, each of these is sort of phrased here in modern form, you know, in terms of, you know, the web and the kind of like metaphors that we build around it. They each have very old roots, right? If you ask like, who is, you know, where can I look to find sort of one of the earliest articulations of the idea of like, we should use technology to create a vast universal library of all human knowledge. Certainly one place that people often look is Vannevar Bush's 1945 Atlantic Monthly article, right? And World War II had just ended, and he was in charge of some non-trivial part of the US science funding establishment. He was asking, what are we going to do with all the scientific knowledge being produced? It's just too much for any one person to understand. The field moves too fast. You can't keep up with the latest papers. Everything is coming apart. Kind of ironic to sort of see someone say that in 1945, when we somehow think of that as a very modern kind of complaint. That was also his complaint 80 years ago. And so he wrote this article, which was remarkably prescient, in that he just described a metaphorical object called the Memex, into which we would put all human knowledge, and we would create links between different items, and we would follow those links, much as the brain follows associative trails in its memory. And he would sort of imagine the creation of like the search industry, the new profession of trailblazers who find delight in the task of establishing useful trails through the enormous mass of the common record, right? So very much this picture of let's use technology to create a universal library. And this metaphor of the crowd, also from around that time, by two of the sort of foundational figures in the theory of mass communication, Eldred Katz and Paul Lazarsfeld, who actually at a workshop in 2004, I had the good fortune to actually meet Eldred Katz at a workshop, you know, very much toward the end of his career, 50 years after he wrote this book. And we sort of compared notes on the fact that like me in 2004, fascinated by things like blogging and social media, he too had been, you know, studying the disruptive effects of technological change on society. In this case, it was radio and the TV, right, mass communication. And their point was that we shouldn't think of the technology as beaming everything down uniformly on all people. Rather, it beams it down on some people more than others, and then often, you know, in a two-step flow of information that spreads between people. So the library and the crowd. But if I take sort of part of their message really, is that at some level, all media is social media, right? We call what we have now social media, but they thought of radio and the TV in 1955 as social media. So if that's the case, then what is new about the media we have now? If it's not the social dimension. And one argument you could make is that obviously modern social media has a bunch of affordances that make it even more socially contagious perhaps, but also modern social media is algorithmic media. Right, that it's curated by algorithms. There's this algorithm that is simply trying to give you what it thinks you want, right? It's just, you know, as they say, it's just trying to make you happy. You know, you click on some things, it gives you more of that. You scroll through your phone, it notices your scrolling speed, it notices that your dwell time on this, the image you ever clicked on it was a little slower than this other thing, so you must have slowed down to read that. Right? It's just trying to find what you want to see. And so there's a sort of first narrative here. The algorithm is creating the environment in which we operate. But a big part of this narrative, and this is very much on the minds of social media companies, you know, much as their, you know, behavior might suggest otherwise, very much on their minds is the idea that the more they optimize, the less happy people seem to get. Right? And the question is, could we somehow understand what's going on there? And the hope is that by sort of 2/3 way into the talk, I will have tried to show you a model in which exactly that connection is happening. that we keep optimizing to show you what we think you want, and the more we do that, the less happy you get. And sort of how can that be? Okay, so that's sort of a first narrative. Algorithms create the environments which we operate. You know, and obviously, the less happy we get, I don't need to convince you that, you know, there are many guys. The fact we have to invent a word called doom scrolling, people joke about being professional internet quitters. People ask questions like, how do I spend less time on YouTube? When some of the answers should be obvious. But we know it's very hard, right? So there's behavioral science. Okay. A second narrative is in one of the algorithms, the outer environment, we live in it, it feeds us things. There's a second narrative, which, time permitting, I'll say a little bit about, which is the algorithm as a partner, right? That we are moving through this environment together, and by our side is some powerful algorithm that's actually helping us to do things, right? And so, you know, things like large language models, as the idea of those as intelligent assistants. And of course, all of the questions that come up there, how do we allocate responsibility, right? If I'm handing off control between me and an algorithm, we have some kind of joint responsibility for what happens. How do we reason about that joint responsibility? So, two narratives, in both cases, the kind of concerns they generate, right? The algorithm creates the environment, but it doesn't really know us well enough to actually make us happy. The algorithm sits by our side as partners, and now we have these fumbled handoffs between me and the algorithm, which, yeah, exactly. Okay, and I'll talk about these two things. I'll talk mainly about this one, and I'll genuinely see sort of whether this will be sort of in a different direction. This will be more theoretical. This is more of a case study of something we built to try exploring this. Okay, let's do the first one, right? Things making us unhappy. So the first observation really is that, and this again, so this joint work with Manish, my former student, and Senthil, behavioral economists, who I've worked with for a long time. We delved into some of the behavioral economics, behavioral science questions here. Part of the issue, of course, is that you don't just have one set of preferences, right? As I scroll through my social media feed, getting more and more stressed out, there are really two processes going on conceptually, right? I'm not talking at some neurological level, we're not going to delve that deeply, but conceptually, part of me wants to keep scrolling and sort of can't resist reading a few more things. And part of me is really unhappy about this, and retrospectively is going to look back and regret this decision. And my point is not that one of these is the real you and one of these is some interloper or some. These are both you. These are both your preferences. They just happen to be two sets of preferences that contradict each other. But there's nothing inherently unrealistic about that. It's just that's sort of how you go about doing things. But we see how that's going to pose a problem for algorithms, because the algorithm watches your behavior and it can't really see the two sets of preferences that are at war with each other. It just sees a single stream of behavior. Right? So there's basically a communication bottleneck going on between you and the algorithm. Even an algorithm that was actually trying, obviously there's many other factors, right? This is an algorithm being run by a profit maximizing company that, you know, presumably does not have your best interest in mind. But let's imagine I built a browser plugin to help me optimize my use of time on the internet. The browser plugin that I wrote is designed just to help me. Even it would face this communication bottleneck. It doesn't quite know when I'm choosing things exactly which set of preferences is going on. So this idea of a war between two sets of preferences, sort of fundamental thing in behavioral sciences, we can kind of sum it up in the difference between, you know, want and should. Right? Two related concepts, right? So we have, you know, food over there, you know, and exactly, yeah. I could have actually just snapped a photo and swapped it in here, but I was more adept at editing my talk with that. So, you know, we go over there, and you know, part of you wants the cookies, and those cookies look pretty good. And but part of you knows you should have a salad. Again, it's not that one of these is correct and one of these is wrong. I mean, we can debate which one we think is a better idea, but both of these are your preferences. Now, we have this with media also, right? You know, you're flying on a plane and there's, you know, 3 hours before landing, you're going to watch a movie. Part of you wants to watch the noisy superhero movie. Part of you thinks you really should watch this fascinating documentary about the font Helvetica. It could, you know, teach you a lot of interesting things. You'd have lots of fascinating conversations about it. I actually do recommend it. It's interesting to me. The people who create this, of course, sort of know they're appealing to the kind of should sensibility, right? You can actually say, you can find here, start watching with your public library card or university login. So deep down, they know that the only people who are pausing and watching this either have a public library card or a university login. Now, these are two kind of, you know, pedagogical examples. These have actually been the subject of a fair amount of empirical work also in the behavioral economics community. So this trio of Katie Milkman, Todd Rogers, and Max Bazerman looked at both food and media consumption and the way in which we have these two sets of preferences. And one thing that emerged, of course, is that one axis along which they really vary is the role of time, right? Because one set of preferences, the part of you that wants the salad, tends to be the part that's capable of planning. It thinks ahead about how you really should have the salad. And later, when it's sort of thinking about whether you're eating nutritiously, it reflects back on how you didn't have the salad. It's able to think over a long time. The part of you that wants the chips tends to operate more in the moment. It's faster, it's more impulsive. It doesn't really think about what its plan was, or retrospectively, it's not going to regret this. It's just going to eat the next chip. And so they actually found, even on sort of much more deliberate timescales, that if they looked at online grocery orders, some get placed to be delivered 3 days from now, some get placed to be delivered today. And the distribution of want versus should actually varies along that time. Similarly, some of you are old enough to remember, and many of you are not, that before we had streaming, we had websites that were mail order DVD sites, right? You would actually manage your queue and things would come in. It was like 2009, 15 years ago. Netflix originally sent you DVDs through the mail. Now, an important feature of that is that the question you therefore asked yourself in 2009 when you were using Netflix as a mail order DVD company is, what do I think I'm going to want to watch 3 days from now? And we all have a lot of aspirations for our 3 days from now self. Our 3 days from now self is going to, clean the house, catch up on all that backlog of email we haven't answered, and certainly watch a documentary about the font Helvetica. Once we went to streaming, and there were good reasons to go to streaming, right? Suddenly there was enough bandwidth to the home to do it. Why rely on the US postal system when you have, but something's changed fundamentally, because you as a user are no longer asking yourself the same question. You're not asking, what do I think I want to watch 3 days from now? You're asking, what do I want to watch right now? And I press a button. I press the button. I mean, it sounds quaint for me to be morphly if I did press a button and start watching the movie right now, but that was the change in 2009. And it was not just a technological change, it was a behavioral change. It was a change in the question we asked ourselves about our preferences. And one thing they found, it sort of half coincidentally, Netflix in 2009 also was running the Netflix Prize competition. Some of you in machine learning remember the influential nature of it, which became famous actually in machine learning also as a privacy case study because they used anonymized data that wasn't, as anonymized as they thought. But there was an interesting coda to all of that, which is that was right in the end of the mail order era. And so all the data that was being trained on, the recommendation algorithm being built, was for my 3 days from now self, those preferences. When they went to streaming, the nature of viewing changed dramatically. And so while the techniques developed for the Netflix Prize competition were still obviously relevant, they're general purpose machine learning techniques, the actual models that came out of that had to be totally rebuilt because you're just asking a different question. It's a different set of preferences. Okay, so these are the questions that we want to think about. Obviously, related to this, right, let's go back to this basic question of platform, that any platform was after. What do users want? So I guess what we've been saying up to this point sort of can be summarized as a fundamental principle of user modeling, often one that's so basic we don't even stop to talk about it, is the principle of revealed preference. We choose what we want, so choice reveals preference, right? This is a sort of principle that's roughly 100 years old in economics, right? In the 1920s, economists observed that it's hard to have people tell you what they want, right? If I were to ask you, like, what kind of food do you like eating? I mean, you would say some stuff, you would try to introspect, you'd sort of forget some things, there'd be stuff you actually know that you didn't think to tell me. Or I could just watch you in the grocery store seeing what you take. And wouldn't that be just a much better way of figuring out what food you actually want? That's revealed preference. And in some sense, all of the digital trace data that we've had all this time is all getting its power from revealed preference. I just see billions and hundreds of billions of clicks, and I'm just forming a model of what it is you want. But what we've been saying so far in this talk, want versus should, is that you don't just have one set of preferences. I'm seeing your clicks as modulated through at least two sets of preferences that are kind of at war with each other. And so the question of, when, how should I interpret that data becomes a much, much harder problem, right? And in some sense, we sort of imagine it varies based on the kind of content. So I'll try to, when we eventually go to build a model, which is, we're going to start in the next slide or so, we're going to want to ask this question about how do I build for a thing where I have two competing sets of preferences? We want to say, like, does optimization work? And as I said, once we set this up, we'll see that actually it's sometimes possible to optimize and make people less happy. But that's not always true, right? In cases where the content does not exploit this wedge between your two sets of preferences, right? In cases where there's this delicious salad that you both eat compulsively and is very healthy, then we don't have a problem. So it's not that we always have a problem. The question of when we have a problem is almost a question that we need to like look for in the data itself. But certainly, I guess what we're saying is like, you're at a party, you finish a bowl of chips, your host takes it back in the kitchen. Part of you hopes they bring out a new bowl of chips. Part of you hopes they leave the bowl in the kitchen and don't bring it back out. But the point is, platform algorithms based on revealed preference, as we've traditionally built them, they will always refill the bowl of chips, right? That's sort of the problem. Okay, so let's talk about building a model. Right, a model of users who have inconsistent preferences. And so we'll kind of add a little bit of math formalism. And actually, even a little bit of math formalism is going to turn out to sort of show us some of what the problem is. Okay, so to keep this as simple as possible so we can kind of process it in real time, let's imagine that a user is consuming a linear feed of content. You're scrolling through a timeline, a playlist, list of videos, whatever it is. So really the main thing here is whether to continue to the next step. We can extend this model so that I get branching choices. It pops up and says, which of these 4 things do you want to see next? You pick one. But for now, it's just a single linear. The user has 2 sets of preferences. We'll call them system 1 and system 2. System 1 and system 2 are these 2 metaphorical characters who populate the landscape of behavioral science more generally. The term sort of was certainly popularized by Daniel Kahneman, the Nobel laureate in economics, who sort of really began the whole behavioral revolution in economics. And they show up in a bunch of places, but for our purposes, system 1 is the sort of fast, impulsive heuristic thinker. It acts first, hence 1. 2, the number that comes next, is the slower, deliberate, more reflective thinker, right? System 2 is capable of planning and capable of reflecting on things. Both of them have utilities. We're going to eventually think about optimizing the utility for system 2, because it's sort of the more interesting one. And it's the one where we might actually ask about, like, are we satisfied with our experience? Okay, so I'm scrolling through my feed. Let's add, in system 1, system 2 are working in partnership because they're all contained inside you. So system 1 goes first because it's faster. And let's imagine item T. We're currently sitting on item T and we're deciding, do I want to keep scrolling? That's the question, right? I'm scrolling, do I want to keep scrolling? Item T produces some utility U sub T, drop-in distribution. For our purposes, because system 1 doesn't really plan, all that really matters is the utility on this item positive or negative, right? Did I enjoy this chip that I'm eating or did I not? It's positive probability P, and if so, system 1 just continues impulsively on the item T plus 1 without ever consulting system 2. Because system 2 is kind of slow to wake up, so if system 1 is in control, it just keeps going. If the utility is not positive, then system 1 temporarily loses interest and hands off control to system 2. So system 2 has one of those rare moments when it can actually make a decision. What should it do with that? Okay, well now here's system 2's reason. So it's looking at this timeline stretching out in the future, it's planning. Item T gives system 2 some other utility, V sub T. Again, in a world where U sub T always equaled V sub T, you would be somebody with like perfect self-discipline who never had a conflict between system 1 and system 2, and then we wouldn't really have this problem. But VT might be the same, might be. Let's say the average utility for an item according to system 2 is V bar. So it's saying, okay, my expected value if I go on to the next step is V bar. What else can I do? I can just leave the site. I can put down my phone, close the app, and get on with the rest of my life. And the outside value of getting on with the rest of your life has value double. So the net utility from the current item is V minus double. The value you get from the item versus the value you could be getting off the site. And that's really what system 2 is evaluating. How much am I getting here versus how much would I be getting if I did other things? Okay. But the point is, it only knows the distribution of items. And so when it thinks about the next item, it thinks about V bar, its expected value minus double. Now, if V bar is less than double, you shouldn't be on the site in the first place because the expected value of what you're about to see is less good than whatever you're going to do if you just go to something else. So you should just never be on the site in the first place. More interesting is what if V bar is bigger than double? So there is value in this next item. So first I need to add one more ingredient because if I really left things the way they are, there would never be a reason for you to leave the site. If V bar is bigger than W, then every time system 2 asks itself, do I want to go on? It would say yes. That can't be it. Because there is one more thing we're leaving out, which is the idea of satiation, right? Eventually, even after eating the most nutritious salad, you eventually just get full. You have had enough food, right? Even after watching the most amazing educational video, at some point you have to go on to something else. You satiate. You have diminishing returns from doing this activity over time. So let's add the notion of satiation. Gradually, system 2 is filling up on content, and eventually they're going to want to. Now, there are a couple ways you could do this. One would be actually deterministic satiation, like there's some exponentially decaying multiplier here that t steps from now won't be VT, it'll be like delta to the T times VT. It's going down gradually. That's actually not so hard to analyze either, but because we want to kind of do the math in real time here in this talk, I'll tell you a simpler one that gives you a similar thing. A really simple formulation would be, in every step, imagine system 2 effectively flips a coin, Q. Flip probability Q. So with probability Q, it says, yeah, I'm still interested, I'm still engaged. With probability 1 minus Q, it is now full, it is done, it would like to be. Okay, so there just comes some random moment in the future when it suddenly satiates and says, okay, I'm done. All right, and it can plan for that. So it knows that the probability it'll still be interested in T steps from now is Q to the T. Okay, so 3 properties of context in terms of this concept, right? One is the expected value for item for system 2, V bar minus W. What is the satiation parameter? Probably Q that system 2 remains interested in. And finally, to take a term from behavioral economics, the Moorishness, probably P that system 1 is in control and consuming a piece of content. Right, so we're in PQV space. We can sort of think about different pieces of content occupy different points in PQV space. Some things are very Moorish, but also very high value. Some things are Moorish and low value. Some things have high value, but very low Moorishness. This is all different parts of space. Okay, how should system 2 optimize its utility? So now let's actually ask, and this is sort of the one place where I'll try to do some math with this model. Imagine the decision problem faced by system 2, right? You're sitting there, you have 10 minutes until your next meeting. There's your phone. You go on social media and just start scrolling, or go on your news site, or whatever it is you're going to do. Start scrolling. Or you could decide not to. How do you make that calculation, right? Qualitatively, you're making the calculation by saying, I will find some interesting things here. I will also end up getting sucked into something I didn't really plan on reading, and I'll end up spending too much time, and it won't be 10 minutes, it'll be like 25 minutes, right? That's the kind of qualitative thing you're considering. This model is expressive enough that you can actually, that's also how the analysis of the model works. It works like that qualitative debate you have with yourself when you have 10 minutes till your next meeting and your phone is right. But I can sort of think of the user's session, right? This is system 2 in planning mode. Is it worth it to me to go on the site? Will I get net positive utility, not on the next item, but over my whole session? So phase 1, so we can think of the whole session as being divided into 2 phases based on when system 2 engages in this on-off transition, right? For the first phase, it's gaining value, then it satiates, and then it's done. So in phase 1, system 2 wants to continue, collects V bar minus W utility per step. How long does phase 1 last? Well, because I chose this very simple form of the model, it's memoryless. So it's just flipping a coin. That comes up tails, so probably 1 minus Q. So the expected number of steps left in phase 1 is going to be 1 over 1 minus Q. The time until the coin comes up. And so that's the expected utility. Now, the coin comes up tails. System 2 is full. It would like to leave. Does it get to leave? Well, not right away, because system 1 might still be compulsively scrolling through content. And so how long is that going to take? Well, now we're in phase 2. And system 1, we're now waiting for a coin with bias P to come tails. So that takes time, 1 over 1 minus P, except we might be lucky and system 1 is done immediately, in which case it's measured. So P over 1. And during this time, you're getting, system 2 is getting minus W utility, because they're getting 0 value. They would like to leave, and they're losing out on their upside option. So that's the trajectory of one session as viewed through this model. I should say, if we had had deterministic satiation, everything would be roughly the same. It's just now we're deterministically doing this. There'd be one slight change, which is system 2's question becomes a little more complicated, because since they know they're deterministically satiating, they might want to leave while they're still enjoying things, because by the time they get back into control, they won't. But that's okay. So I add up all the utilities, and I get this is the utility for system 2, right? So it's V bar minus W over 1 minus Q, that's phase 1, minus V W over 1. You can think of it sort of as something over 1 minus Q minus something over 1 minus Q, right? The denominators of the main pattern. Okay, now let's go all the way back to what the platform sees. This has been all a story that's gone on inside the user's head, right? If they're trying to solve this decision problem. If they go, do I want to spend the 10 minutes before my next meeting scrolling? Now let's go pull back and say, what does the platform see? Like, what are they observing when all this is happening? Well, they're seeing the length of the session, right? All they see is how long did you scroll for? And that's essentially their engagement metric, right? So if we go back to, now I should say part of the point of all of this modeling is that it's sort of happening in conversation with platforms that are understanding that engagement metrics on their own are really much too superficial for the kind of complicated behavioral effects going on. Right, so but if you go back to sort of classical engagement metrics as people conceived of them in social media, it was by and large session length was your proxy for engagement. Right, you would have a meeting with the UI team, and they'd say last month the average session length was 12 minutes, and this month it's 13.5 minutes. Engagement is going up. Right, that's this. We can see these two things are different, right? So we now have these sort of two governing equations: the utility and the engagement. Right, the platform sees this, you experience that. And what's happening here? So both of them are something of 1 minus q and something of 1 minus b, but the signs are different. That's the key point. Because if I know engagement and I'm trying to reason about this, what can I do? Well, first of all, if p is 0, then these two second terms aren't there because there's a p in them. So I just have v bar with double over 1 minus q, which is sort of reconstructing why engagement was always viewed as a good proxy for utility. Because if I don't think about behavioral conflicts, then you're getting value from being on the site, otherwise you wouldn't be there. And the longer you're there, the more value you get. But if p might come from some large range, and I don't know what range it's coming from, then I have a problem, which is that large engagement could be a sign that the first term is large and the second term, but these have opposite signs in utility. This term being large would be great, this term being large would be bad. And I can't tell that from just knowing that the engagement is large, right? It's underdetermined. And so that is this notion that I can't tell whether it's causing happening or not happening. And of course, if p is large enough, this becomes negative. And this is always being matched with 0, because if system 2 knows it would get negative utility, it just won't do that. And we'll just use the site. Okay, so now this model now with this pair of equations lets us get at this high level point I was suggesting at the beginning, which is this is now a model expressive enough to capture the idea that the more the platform optimizes, the less happy the user gets. Let's see what that actually might look like. So the platform has to select what kind of content to recommend, right? What is the mix of content it's going to put in here? And it can measure the engagement, T, not utility S. And the question is, what is the effect on utility? And what it is actually depends on basically the shape of this feasible region. So let's see what that would look like. And again, we're imagining the problem is even manifests itself even when I have essentially a platform whose entire goal is to increase your utility. Right? Obviously, there are many other problems actually happening, including the profit motive of platforms. Their interests might not be aligned. But again, I'll come back to the point that to understand the nature of the problem, we have to understand that all of those are on top of this even more fundamental problem that even if you built this thing yourself to watch your own behavior, you would have this problem. Okay, let me show you a simple example to kind of show you what happens here. And then there are much more complicated examples that we did into the paper. So this idea of a content manifold, right? So I could create some kind of content. There's some parameter that controls it. Imagine I'm trying to figure out the mix of content in your feed, and I have this knob called X that I can turn, which varies the kind of content. I'm not quite sure what X does. I just know that when I turn it, you behave differently, right? What actually is happening, unbeknownst to us, is that the content looks like the knob basically changes people. Right? It's just raising the Moorishness of the content while keeping the quality actually. It's not making the content worse. Content's still good, but it's becoming more Moorish. What's going to happen as I vary P? Well, if I think back to our equations, the engagement's going to go up. If we have this, there it is, 1 P. But the utility has this negative term. So it starts high, because there's a lot of value. But I'm just burning off utility as I go. And so I'm turning this knob and I'm seeing more and more engagement. And indeed, we have exactly this dichotomy that the more I do this, the less happy the user gets. Of course, I can't detect that. But one day, I accidentally walk over this cliff. Because one day I'm here and the user has negative utility and they just don't show up. Right, so we have this dynamic where the user is spending more and more time, and then one day the user's like, I just waste way too much time on the site. I'm through with it, I've deleted the app. And they're gone. And so this is the kind of situation that you want. Now, we can make more complicated things going on, right? So in particular, we could imagine I read this. So maybe the quality actually also goes up with this. Maybe this knob actually makes it both more Moorish and also actually makes it genuinely more enjoyable. Then this utility curve would tilt so that actually initially it's getting better. For small values of X, we're actually improving. there's a global optimum. But then beyond that global optimum, it comes back in. Right? And the challenge for the platform, even if it's just trying to make you happy, is to figure out when it is at the top, that peak, and when it's now gone too far. It's actually okay. So this is the basic model. I think it casts into relief the question that now, we would have to think about. It also sort of lets us think about a bunch of design choices that we can consider. So let me tell you some of those design choices, and then because we have a little time remaining, I'll move on to the second part of my talk, the algorithm as a partner, which will be on a different lab work. So, right, so we start with this, we're optimizing people get less happy. We have this model that basically has that property. And there are various design choices we can think about. So a lot of this has been about so far how to interpret the data that we collect. Right, I see clicks, I see length of time spent, and I'm not seeing user utility. It's a problem. We can first ask, what could we add to this? So one is the role of surveys, right? So these surveys pop up when you're on the internet. A survey pops up saying, how are you enjoying YouTube today? Excellent, very good, good, fair, poor, and then you X out of the survey and you don't answer it because you're watching videos. And that's of course what most people do. But with hundreds of millions of people doing this, some signal does come in. You can think of those surveys actually as the platform trying to talk to System 2 directly. They're basically trying to reach out through the screen and say, excuse me, I would like to speak with System 2. Are you having a good time, right? And in fact, you can imagine that actually looking at the answers to those surveys is a function of the length of the session, right? How far into your session are you? Might actually tell me something about this. It's sort of a special case of the general premise that we would like to look for cases where we think System 2 is speaking, right? Clicking is, heavily dominated by System 1. Answering surveys is not, but other things are not. Like blocking or muting a piece of content. Clicking a button that says, don't show me content like this again, is a planning activity. It involves thinking about the future. It tends to be not something that System 1 spends a lot of time doing. It is a very System 2 kind of activity, right? So it's possible that those kinds of features, muting a user, blocking content, are things that we should actually treat in a sense separately, right? When we're thinking about this, we should think about this as representing part of the conflict. There are even kind of natural experiments you can do. You're scrolling along and then the app crashes, right? Now the app crashes, it's up to System 2 to decide I'm going to reopen the app and keep scrolling, right? That's an obvious moment when if you are just compulsively scrolling, you now have a chance to leave. So that's something else that we can actually look at. Okay. I've been talking about a linear timeline. Obviously, a number of options to display is sort of a two-edged thing. It gets more complicated. We can put that in the model. On the one hand, we're now taking the max of all the value of what you see, so the value is going up because I can pick the best thing. But also, there's even more chance System 1 is going to find something engaging and keep going. So there's this tension. A lot of behavioral economics on the subject of self-control problems with System 1 involves the issue of frictions. How much friction do I add in your actions, right? How easy is it to take the next chip? And so, for example, things like preview versus autoplay, right? Do I have to actually ask for the next video, or is it just start playing immediately? It is a lowering of friction, which makes life easier. There's also this issue of the benefits of enforced breaks. Right? So I talked about like the app crash, which you have to come back from. The metaphor of the app crash was actually sufficiently powerful that actually some platforms now have added to their profiles, and you might see this on Instagram or TikTok. You go on your profile and you can configure it to say, every 15 minutes, I would like a 30-second break where nothing happens. Right? So you're scrolling, and at the 15-minute mark, or you can install a plugin that does this for you. At the 15-minute mark, basically the thing freezes for 30 seconds. Now, for a platform that's obsessed with user engagement and preserving the kind of flow of activity, why would you force the user to sit there for 30 seconds? And the answer is it's actually trying to impact System 2's planning problem, right? The platform knows that people are saying, I'm deleting this app because I waste too much time on the platform. Knowing that 15 minutes in, you will have a chance to consider, is this a good time for me to leave, can actually change that calculus. And actually changes the need in this optimization problem, right? So we can create situations within our model where adding a mix of content that has zero value and zero Moorishness can actually change System 2 from deciding not to be there to be. And finally, the unexpected effects of embedding media and other content. So there's this overarching question of who controls the decision to go on the platform anyway, right? We sort of think of it as it's System 2 that decides this, but various decisions you can make tilt the balance of power, right? So you might decide you don't watch YouTube videos because you spend too much time on YouTube. You've learned never to go on YouTube, but you do read, say, the news, And so you're scrolling through a news article, and embedded in the news article is a YouTube clip, which starts playing. And so now, even though System 2 knew not to go on YouTube, and instead to read the news, System 1 is already watching the video. And now you're sucked into YouTube, right? So this idea that we can actually create design choices that tilt the balance of power is something that we see in a lot of online media. We also even see it back in the physical world, right? If we go back to our metaphors in terms of food, you walking through the airport concourse know not to stop at the place that sells the 1,000-calorie cinnamon rolls that are bad for you, because System 2 is, has too much self-control for that. But the cinnamon roll place knows that also, so they pipe the smell of the cinnamon roll out to the airport concourse. So as you're walking through the airport, in your mind, System 1 is already eating the cinnamon, right? Again, this tilting of the balance of power, right? This embedding of one kind of medium in another, and that's something else that we can. Okay, but the time we have remaining, I want to talk about this other structure that I suggested at the beginning, the idea of the algorithm as a partner, right? So there are a lot of interesting cases where we can imagine we're navigating this environment. We have a partner who's with us, some powerful AI that we can interact with. There's some work on this in the context of media consumption. So my colleague Gordon Pennycook at Cornell, working with David Rand, former postdoc advisors at MIT, it's very interesting work on AI assistants to try to help you understand whether the news you're looking at is either correct or conspiracies and so forth. I want to talk about some other domains where we can think about this. So again, this is algorithms serving as partners, right? The algorithm is your partner in writing code or writing text. If we think about autonomous vehicles, the algorithm is your partner in driving. And the question is like, what is it going to look like when we have extremely powerful algorithms working as our assistants? Now, part of what struck us when we think about this in the context of media consumption, we think about it for coding, for driving, we have cases where they're very useful as tools. They also have their weak points. They sometimes are wrong, but we also often think about the truly superhuman case, right? The algorithm is truly superhuman and you're working with it. And it can do everything better than you. The only problem is that you may not understand everything it's kind of telling you to do. The problem with that kind of conversation is that it tends to be speculative. It tends to have a sort of sci-fi dimension to it, right? We ask, what will the post-human mathematics look like when machines are better at proving things? What will post-human music composition look like? And we sort of debate, are we ever going to even get there, right? Will we have post-human, are we going to have a post-human era in math and music composition, right? There's sort of a lot of science fiction. And so we asked ourselves, and again, now I'll move into some joint work with Ashton Anderson, University of Toronto. Two of his students read McElroy and read Made, and that's at Microsoft Research. We're curious about these questions, and in particular, a domain where could we find a domain where this isn't science fiction, where this is actually happening, right? A domain where we have high levels of human mastery and scholarship, right? People train their whole lives, like concert violinists, to achieve this amazing level of mastery that fills other people with awe, where we have like 100 years or more of scholarship, libraries filled with the site of the subject, like mathematics or music performance or whatever. And yet, despite all of that, algorithms have just completely surpassed it, where the singularity arrived and we're now beyond. And there are domains like this, and one big one is chess. So I want to spend the final 10 minutes talking about chess, because it's a domain where we can take some of our science fiction questions about superhuman AI and genuinely ask them. Because the point with chess, just to kind of give some of the history here, right? Obviously, we're not the first people to think that chess is a good model system. Chess is one of the few, maybe the only domain to have been metaphorically called the Drosophila of more than one subject. Right, the Drosophila, the fruit fly, the model organism of genetics. Herb Simon and William Chase famously in the 70s said, well, just as the fruit fly is the model organism for genetics, chess is the fruit fly of psychology, because anything you want to study in psychology, you can study most easily and most malleably in chess. And John MacArthur famously called it the Drosophila of development. And we want to argue that it's now becoming a sort of Drosophila of a third thing, which is machine superintelligence. We have very few domains where we have genuine human mastery of something, and also genuinely superhuman AI that's even that far beyond that. And chess is super, right? So just to give a sort of brief history, right, 1980s is when chess engines first began beating human grandmasters. Early 90s, people held up this hope that, okay, it beat human grandmasters, but maybe there's something special about the very best humans in the world that computers will never catch up to, which is really a remarkably naive belief in retrospect. So 1997, probably the moment when the most people in the world pay attention to computer chess, Deep Blue defeats Garry Kasparov in this sort of, this summoning of Mount Everest, this milestone. But of course, the point is, the performance of humans was kind of going up over time very, very gradually. The performance of chess engines was going up very sharply. And so 1997 was just the moment when they coincidentally happened to cross, right? They kept going up. And so the last time a human ever beat a chess engine sitting at a desktop computer was roughly 2005. By 2007, they could do what sort of, grandmasters do with the amateurs. They could concede a pawn at the beginning or a knight at the beginning and still win. And of course, it kept going, right? 2018, computer chess was back in the news because these things were all handcrafted evaluation functions, whereas AlphaZero using deep neural nets actually taught itself to play chess and tuned its value function purely through self-play. Quickly, the open source community created an open source function called Leela. Okay. Yes, we have some stuff ratings here, right? All of this can be put on this one-dimensional spectrum of chess performance, where ratings 1800 is sort of a strong amateur, 2800 is the best human player in the world. Chess engines are way beyond 3300, right? They're as far beyond the human world champion as the human world champion is beyond any amateur. Okay, so we were interested in this as an ecosystem for thinking about superhuman AI. We wanted to think about situations where you could put the superhuman AI, like Leela, which would be our kind of example here, together with a human and try things. But of course, if we want to try things experimentally, it's going to be hard to, have Leela and a human kind of sit there and do some training loop because there's only so much human patience people have. So it's interesting, if we want to study this ecosystem, to have something that serves as a kind of proxy for the human. And so the first question we asked was, can you build a chess engine that's not trying to win chess games, but rather is trying to match human performance in chess? So we took Leela, we took the head off of Leela, the evaluation head that tries to make good chess moves, and stuck on an evaluation head that simply tries to, as accurately as possible, play the moves that a, say, 1500 rated chess player, which is using all this computation to try to act like you when you play chess. And we have a ton of data, because on sites like leechess.org, which is a fully open site, we have billions of games. Games are public by default. So we have hundreds of billions of chess moves to train on. We train a chess engine called Maya. It starts with Leela and just replaces the head to try to match move performance. And we try one sort of for each human rating. If you're doing it right, then basically, there's a Maya rated 1200, which matches human performance best at 1200. And as you move away, it matches it less well. If you're trying to match 1500 players, you could do a little less well, 1600, well, 1700, so forth. And of course, you want to make sure that it's actually matching things better than if you just take a chess engine and dial its performance down to some low level, right? The reason you're able to have interesting competitive games with a chess app on your phone is because you dial down search depth, right? And somehow by some intermediate value calculation, there'll be some depth where it's so weak that you and it play competitively. But that's very different from saying that it makes the same moves that you do. It just plays chess better. And that's actually what you see in the data. So this is move matching performance on all of this. So the so what's going on here is these are the Maya engines. They form this kind of string arcs. This is Leela. This is Stockfish, which is another open source chess engine. Right, and so if you actually train for move matching, you're going to do much better. Okay, and you get things again, knowledge of chess not worth here, but you can take actual positions and sort of discover what is the rating in which people discover the good move. Right, Stockfish, a chess engine, just says, well, the best move is this. Whereas Maya at the different ratings says, well, until 1500, people tend to want to do this move, and then beyond 1500, they actually find this. Right, so we can actually go in and take positions, actually say what is the difficulty of this move, as determined by which Maya is the first one to predict that's what you're going to do. So we released this on Leechess. Actually, it became the most popular bot on Leechess, so it's now played several million games. People do kind of report that it is kind of more human-like. An intriguing thing actually is it does not play, like the most popular version is the 1100 rated Maya, so Maya 1100. Curiously, Maya 1100 on Leechess is not rated 1100. It's rated higher. There's a whole digression we can go into there. Roughly speaking, it's because the way people seem to enjoy it the most is it produces a distribution of what the human is likely to move. It takes the highest probability. So it's always picking the argmax, right? Always make the most likely move rather than sample from the distribution. It turns out if you take something rated 1100 and you have it always make its most likely move, it'll play actually at about 14 strength. Because that's arguably probably true of humans also, right? A lot of the reason why you end up with the rating you have is because you lose games making moves with mistakes that you wouldn't normally make, right? You typically wouldn't have made a mistake, but this time you did, right? So it almost says if you can take a level-1 player and say, always make the move that you are most likely to make, that if you could run history 10 times, which one would you make the most times? You would arguably play better than your average player, right? That's really what's happening. Okay. We did all this. I wanted to use it to ask the partnership question. Right? So we took Leela, this superhuman, I mean, unbelievably powerful chess. We retrained it to say, try to play like a 1500 player or an 1100 player. And so I now have Leela and Maya. And I can ask about partnerships between Leela and a human, or now as a proxy, Leela and Maya. Like what happens when Leela and Maya try to solve a problem jointly? So there are many questions we can ask about partnerships. I want to zero in on one where we can say something interesting, which is the danger of sudden handoffs. Right? So in a lot of situations, we have a flow of control where the superhuman automation is doing something, or the AI automation, whether or not superhuman. And at some moment, it goes offline, it shuts down, it turns control back over to me, right? We imagine we're driving and the autopilot goes offline, I can take it. Or I have a fleet of self-driving taxis and I'm sitting at a dashboard watching 10 of them, and I'm supposed to intervene as a human operator if it reports something you can't. You imagine a partnership in conversation. Me and a chatbot are going to a negotiation with somebody. We're having this joint conversation, and the person asks me a question. I'm not quite sure, the chatbot's been doing the talking. I'm not quite sure what it had in mind with this whole line of conversation, but now I have to speak for myself, right? This sort of handoff between the human and the AI. And so the worry is that a powerful AI that's optimizing for itself might be constantly setting you up to fail, right? It knows what it's doing, but when it hands off to you, you're not sure how to follow up. You're not quite sure what to do with the car when it hands off to you. And so what you really like is now doing both powerful, but always lets you take over in some graceful way. Okay, sudden handoffs is interesting. As we began thinking about sudden handoffs, we realized that like a lot of fiction is obsessed with the worries about sudden, like certainly a lot of literature I read as a kid. You've got like the Lord of the Rings. This is the Fellowship of the Ring, 9 people, and the powerful wizard Gandalf, who just convinced them to embark on this unbelievably dangerous mission in which they go into enemy territory, throw the ring of power into a volcano right at the end. And they're all looking a little scared, but they're like, it'll be okay because the all-powerful wizard Gandalf will be with us. Except 2 chapters later, Gandalf vanishes for the rest of the book, leaving all of them on their own to carry out the mission they have for this. And over here on the right, we have Linda, the Good Witch of the North, and the Wizard of Oz, who has convinced Dorothy to take a unusually aggressive negotiating position with the powerful Wicked Witch of the West. And Dorothy, of course, is terrified, but she's like, it's okay because Linda's here to help me. Except 5 minutes later, Linda vanishes for literally the rest of the entire movie, leaving Dorothy on her own to carry out this, right? So for whatever reason, we as humans worry a lot about being set up to fail by powerful partners, right? They have a plan, we start following it, and then we have no idea. And so the chess context lets us actually look at this in the context of actual superhuman AI parenting. Imagine you and Leela sit down and play game chess in this kind of like Dorothy Gandalf kind of situation. And what we're going to do is say, on each move, the two of you can't communicate. I'm going to flip a coin to decide who makes the next move. So what's our concern? That Leela sees a brilliant attack that begins with sacrificing a piece, and Leela makes that move. Leela is just Leela. Leela's oblivious to the fact that it has a partner. We flip the coin for the next move. Now you have to follow up on it. You have no idea what to do. So he makes the move, and now Leela's like, what are you doing? Now the attack is gone, and we're just down a piece. Right? It set you up to fail. It didn't realize it was doing it, but its thinking was just too abstruse. Right? So when we do this with Maya, and this is in this work we had at ICLU this past year. And actually, we see this happen. Like Maya keeps losing because it doesn't know what to do in the situation. So we ask ourselves, this is now a model system where we can actually try to train a better kind of partner. Could we train a partner for Maya that would be a Leela Maya team? Now you try some baseline. You try putting like Maya here. So a Maya partnership is just Maya. So it always has continuity. But it has the problem that it loses to the Maya partnership. It turns out even a powerful partner who regularly sets you up to fail is still a better teammate than just yourself in this situation. But it turns out through self-play, we can train this partner bot, which actually beats Leela Maya teams. It turns out it plays very strong chess, but it always sticks to positions that are understandable to its weak partner, right? It's a kind of skill-compatible AI, right? So team with Maya, it wins 66% of the games, even though on its own, in solo competition, it only wins 14% of games, right? It's weaker than Leela. It's quite strong. To beat Leela ever, you have to be incredibly good at chess. But it's certainly weaker, but it's better as a team. Okay. So with that, I want to wrap up. We've been talking about these sort of two ways to think about algorithms. As creators of the environments that we're in, powerful partners as we traverse those environments. I think, a lot of this sort of speaks to just the profusion of fascinating questions that we're currently faced with, right? In some sense, the frontier of things that we're looking at with powerful algorithms and AI is only widening. These are two of the ways that we think about using it. But I think there's a lot of room for work that really crosses between, different areas of computer science, both theory, AI, experimental work, and then also engaging with the behavioral sciences to try to understand some of what they know about human behavior and human performance. So I think it's going to lead to a lot of really interesting opportunities going forward. Thanks very much.
Are there questions? Questions on the. Oh, you have a.
So let's say like a human is trying to learn chess, and then like they have a partner board, and they can when they're not sure, they can have that. They can just ask the partner board like what's next.
Yeah.
Clearly, like you're starting out and maybe you're in 1,000 elo. Like if your partner board is too advanced for you, then you probably learn nothing.
Yeah.
Do you think there's like a gradual inclination where like as you improve your partner board, also you just choose a better partner board and then that gets you off a path?
Yeah, it's a great question. So, right, one of the potential implications for all of this is for teaching. I totally agree, and that's one that we're sort of trying to explore a bit in the chess kind of like what is good for training. Yeah, I think. Right, so there are different kinds of partnerships, right? One in which you're just alternating moves. It's here. One in which you're you're actually allowed to consult it. It's can tell you things. And yeah, there is a sense of like trying to show you the right level of difficulty. One of the ways in which we actually think that like tools like Maya can potentially be helpful from an educational context is, often people when they play chess, they go back over their game with a chess engine, and it shows them where they could have made a better move. But those better moves that they could have made come in two flavors: moves that they plausibly could have found, and moves that they never ever could have found. And what you need for separating those out, like the ones you should focus on are the ones you plausibly could have found. But to do that, you need some notion of like, what is the rating in which we predict someone would have found this move, which is sort of exactly what Maya is doing. So one thing we're doing is creating some chess analysis tools that actually basically annotate each move you could have found with the rating at which they think you could have found it. And then you should basically focus on the ones, as you said, that are sort of slightly beyond you as potential source of improvement. And we're sort of at the moment working on some things to see how much that can actually help you. Yeah.
In like part one of your talk, you're talking like how you might give into impulses and then the social media people only see that engagement and then suddenly like it drops off. Is there a way for them to measure like the system to utility function? Like
it's a huge challenge. So right, a couple of things I was mentioning sort of our beginnings of that, although there's much more to do, right? So like something I mentioned like surveys or are certainly one way to try and get system two. Looking at actions that involve like blocking of content or muting of content tends to be a system two action. But these are all, as you're observing it, that's not a robot. That's kind of cherry picking things I can do. I think this is a fascinating open question. Is there something in the signal that might be actually telling me something about, like, is information about system two sort of leaking through in just the pure click signal? I don't have a sort of principled argument that says that's impossible. Like that may actually be there. And so I think it's really an interesting question of like how much information is actually in the signal about system two. It's a very nice open question.
Thank you so much.
Fascinating talk, John. I have a question about part one. If you think about the social media provider, they're creating content, but they have a different objective function to maximize, right? Suppose they're maximizing their profits, actually the orange curve that they're maximizing. So in this case, like their best maximum utility is at the very top of over there, right before the user leaves the platform.
Yeah.
is there a way of, breaking out of this issue? Maybe competition, maybe avoiding monopoly?
Yeah, it's a great question, because, in the same way that like when you first learn intro microeconomics, you discover that products are priced at the margin, which means you're gonna end up paying exactly what it is valued to. So somehow the company is managed in a monopoly setting to burn off all the surplus. Whatever surplus this product was gonna give you has been burned away by them pushing the price all the way to the edge. Whereas social media is it's free, you're just there. And so where's the part where they're burning away all your utility? This is it, right? This is that same thing, they're pricing at the margin. They're gonna push your engagement to the point where you've burned off almost all the utility into this model. And so, yeah, I think, so it's certainly a reflection of that same kind of principle. I think I think competition is certainly one of the main things we're thinking about with regard to this, that in principle, if I have two competing platforms, then I'm gonna pick the one which gives me higher utility, which is gonna cause them potentially not to want to push me all the way. And then there's these interesting things, because if my revenue is coming from advertising, then advertising revenue is growing linearly. But of course, I'm only gonna pick the one which gives me higher utility, so you want to pull back from the absolute brink of that precipice. And I think there's some interesting optimization problems that are are going on there that I think, but certainly the role of competition is a big one.
More questions? Other questions for the team? Okay, then let's thank Jon.
All right.